So here's an example of using trigonometric substitution. It's a little bit more complicated than, say, your most basic examples, but it doesn't have all the difficulty that they could have. It's somewhat inspired by a problem in Stewart. So he has a certain electrostatics problem, and I wanted to modify that a little bit, but still have the same idea. It turns out that a lot of things in electrostatics, just like distributions of charge, electric fields, have to do with a 1 over a 3/2 power of a quadratic. It's like a 1 over r cubed kind of thing. And suppose that our problem led to exactly this integral. How do we want to do that? Well, when you have this situation where you have an odd half power of a quadratic, this is the cube on the bottom here. That's the cube of the square root of x squared plus 16. So it's based on the square root of a quadratic. Very often you want to do trig sub for that. You do want to see if you could use a regular old simple substitution or u sub for that. If this were an x on the top, you could do that because that x dx would be very close to the differential of x squared plus 16. So don't always reach for u sub, or reach for trig sub. But here, it's an x squared. That's not going to work as well with that kind of substitution. So, so we're going to go to trig sub. Then the next thing is, what type is that quadratic? It's an a squared plus x squared, constant plus x squared, and that means it's going to be a tangent. And so the basic identity we're going to be taking advantage of, the crucial part of it, is 1 plus tangent squared equals secant squared. So you could look up various memorized formulas, things like that, but the basic idea is we want to take that x squared plus 16, that is not a 1, so that doesn't match this 1 yet, and we're going to want to factor out the 16. So it's interesting here to me that the crucial part is to get the constant term right, which is a little weird because usually constants are like, oh, who cares? But it's really crucial because this has to be a 1 plus for that identity to be activated. So factor out the 16, the constant thing. See what happens. Well, then that turns into x squared over 16. So then I just have to pattern match. Okay, 1 plus something squared. Oh, that's plausibly going to match 1 plus tangent squared. Okay, so I'm going to do a little bit more rewriting. I'm going to rewrite that as the quantity x over 4 squared. So if you can get it as some constant, a multiplicative constant, times 1 plus something in terms of x squared, then that tells you we must set x over 4 to be tan theta. Usually you're just going to go ahead and rewrite that as x is 4 tan theta. Okay, that's our crucial first breakthrough. That's the substitution that should, in principle, work. Always just do the dx right away. Don't forget that. So that's going to be 4 secant squared theta d theta. Okay, so let's see. Now you just go back up and see if I got enough of a sidebar calculation to put everything in. I know what the dx is. I just said what x is, 4 tan, so we're going to square that up here. And then we've designed it so that x squared plus 16 is going to be nice. Okay, let me just put that in here. By design, x over 4 is tan theta. So I always like to really do this calculation and see the identity work and just double check that it's really going to work out. Okay, yes, that's 16 secant squared theta. Okay, good. So now I'm going to start a new display math here. And what about the 3/2 power of that? This is the whole point of why we did this, is the 3/2 power of something complicated is not real fun. But that 3/2 power is then going to be the 3/2 power of the 16 secant squared. And when you take something square and then a half power, those basically cancel out. So 16 to the 3/2. Well, listen, let me just write it all out as the square root of 16 secant squared theta to the third. As I pointed out, that's really what's going on. Okay, square root of 16 secant squared theta. Now, this is where it's a little tricky. Most books and most AP problems will not try to trick you on this. But it is something a little bit dubious. I squared and then square rooted and assumed that they just cancel out. Okay, that's going to make sense if I can assert that, that secant theta is greater or equal to 0. If not, I would need an absolute value and it'd be a pain in the butt. Okay. Now, luckily, you can do this kind of substitution. I don't want to belabor this, but you can do a substitution x equals 4 tan theta, And you can choose thetas so that secant theta is guaranteed to be positive. So it turns out, if you do it right, I'm not going to do a definite integral example right here, but whatever the limits are, you can do it so that this is satisfied. So the quick and dirty is that the tangent substitution, you shouldn't really have to worry about weird things with signs and absolute values. Okay, so, all right, so now we're good. That's the denominator. The numerator is going to be okay. I'm just about ready. So let's put it in, put it all together, and we'll see if, that's a little thing for later. Okay. So that is going to be the integral. Okay, x squared is going to be 16 tan squared theta. X plus 16 to the 3 halves we just discovered is 64 secant cubed theta. That's just this guy with the cube all cubed out. And dx is right here. I'm just going to copy and paste. Okay, now we just simplify. As it happens, the 16 times 4 equals the 64. Kind of a slightly random thing. More interesting, secant squared cancels out 2 of the secants on the bottom, and so we get tan squared still on the top over secant theta. So now we're at the next phase, which is we've got some sort of trigonometric integral. This is one of the reasons we do some practice with those particular integrals in our book 7.2, so that we know how to do trig sub, so that when we change this algebraic thing that's really quite awkward to a trig, we're not just stuck. So we have to think about this a little bit. So again, remember one of our key things is trig identities. We've got tangent and secant still in the same expression. And a 1 over secant wouldn't be bad. That would just be cosine. And so what if I just change that tan squared, use the identity one more time, and just change that into secant squared theta minus 1. All right, so we used it in a slightly different form. We know that 1 plus tan squared is secant squared, so whenever we see tan squared, it's secant squared minus 1. Okay, so that was a nice little break. Okay, and that's not hard. That's going to be secant theta minus, okay, I'm just splitting up the numerator. Very common thing that people forget to do is you can just split up a numerator if it's convenient. That's going to be secant squared over secant, which is secant, minus 1 over secant, which is cosine. Okay. Now, we would still be stuck if we hadn't already done the integral secant theta. That is one of the trickiest ones, but we're going to assume that you've already seen that, or you can look it up on the table, something like that, and that is log of secant plus tangent. Log of absolute secant plus tangent. Okay, oh, and I don't need the integral anymore. I am doing the integral right now. This is the antiderivative, and then, of course, minus sine theta plus c. Okay, so we're not done. Since this was an indefinite integral, I do want the answer as a function, and of course I want it as a function of x, unless I can convince the person I'm doing it for that this is just a better way to think about it, which could happen, but we want to have the skills to translate it back. Okay, so we need to know how secant theta, tan theta, and sine theta all are expressed in terms of x. So that's where often a picture is helpful. What was the substitution we made? Remember, the substitution was that x over 4 was tan theta. This is where it's nice to have it in the form where the trig function is isolated on one side, because that tells you how to draw a triangle that encodes this exact information. This is a picture of a right triangle. Well, I should have put a right triangle mark here, sorry, where tangent of this angle is guaranteed to be x over 4, because I put x here and I put 4 here. Pythagoras then tells me that the hypotenuse is root x squared over 16, or root x squared plus 16. Not surprisingly, that's exactly the key thing that we were trying to deal with originally. That's always going to happen. Okay, and so let's see. We need, what do we need? Well, tan theta, we already have it. It's x over 4. We're done with that. We need secant theta and sine theta. Sorry, I keep flashing back and forth. So secant theta, 1 over cosine, or hypotenuse over adjacent, that is the root x squared plus 16 over 4. And sine theta is opposite over hypotenuse. That's going to be x over root x squared plus 16. Okay, so armed with that, let's just copy this back down. So our final answer is going to be, actually let's copy the original too to make sure it's a complete interesting statement. Give me a sec here. Okay, and so that is going to be, oop, I went a little too far. There's my notes here. And it's going to be natural log of, copy paste, all that stuff, plus x over 4, and then minus the sign, which is this puppy. Okay, this is a very substantial answer. It's got the square root of x squared plus 16, not too surprising, but it's also an ln. It's got another copy of x root x squared plus 16. This is not guessable. No way. I've never seen anybody guess something this substantial. And it's it's really a non-trivial thing to get from here to here, and the best way to do it usually is a trigonometric substitution. But we're done.